Then we can have a second look on this task 20 that we have already solved with superposition. So now I will take a second color green for task B. So we should solve this circuit once again with the help of branch current analysis, and we already did it before with superposition, and for superposition we got a result of 7.2 ampere for this current here, and we only calculated this current. So yeah, what would be one advantage of this branch current analysis over the superposition method? That we would calculate all the remaining currents here, all the unknown currents. And so how many unknown currents do we have? In total, I would say we have 4, because we have these 4 resistors. So we could set up a system of equations with 4 equations and 4 unknowns for these 4 currents. Yeah, depending on, however, what you do here in this branch current analysis, you might also end up with a system of 6 equations and 6 unknowns. What would be the other 2 unknowns in the circuit? If we go from 4 unknowns to 6 unknowns?
Source voltage.
Yeah, the voltage, we know, of course, we know the current here and there, but we don't know the voltage drop across these current sources. Okay, so yeah, but how did this branch current analysis work in general?
Set up KCL and KVL.
Yeah, so we would need to set up Kirchhoff's current laws, and we need to set up Kirchhoff's voltage laws. And as discussed in the lecture, they need to be, so each of them, they need to be independent of each other, and each of them, they need to be independent of each other, because otherwise you have dependent equations in the system of equations, and this will not help you in solving this system of equations. So how do we get independent Kirchhoff's current laws? And yeah, there's an idea.
We have 4 nodes, so we have to we set 1 as ground, and the other 3 are the...
Exactly. So we count the number of the nodes, and we have 1, 2, 3, 4 nodes. So we can say, okay, K equals the number of nodes is 4, and we always have K minus 1 independent nodes. So we need to find 3 nodal equations or 3 Kirchhoff's current laws, and we can just do it, let's say, for this node, maybe this node, and this node. So for the node A, and I need more current directions, let's also use this current flowing downwards, and this current flowing downwards, and this current flowing downwards. So for the first node A, our Kirchhoff's current law would be exactly. So I will directly try to order them: minus I1, minus I3, plus IS6, or I want to have the sources on the other side already, so I will write it like this: IS6, the current that goes onto the node is the same as the sum of the currents that go out of the nodes. Okay, so then for B, which is this one here, do you want to directly continue? Exactly, is the same as IS5. And for the node C, exactly. So this is also a 5 here. Okay, and so then we have three equations, and if we would once again calculate the sum of these, then we would end up with the Kirchhoff's current law equation for the last node, because this is a dependent one. Okay, so then we would need to set up these Kirchhoff's voltage laws. And yeah, so how do we do this? Or how do we find independent ones? Do you remember the method from yesterday? So what would we need to set up to find independent Kirchhoff's voltage laws? Yeah, there was this method with this complete tree. We were looking at the graph of this network, and we would need to find a connection of all the nodes, but there should not be a complete circle. Okay, and so one option to do this would be to use, for example, this connection. Right? Because this would be a connection of all the four nodes without having a complete loop. And so now you could do it like this, no problem. And then we would close this complete tree over this branch here, over this branch, and over this branch, and we would get three additional Kirchhoff's voltage laws. And so we will get 6 equations for our 6 unknowns. And in this we would also have the voltage drop here, and of course we would also have the voltage drop here across this source. There's a question, or there's an idea?
No, just a question. So the current source IS5 is considered to be there for that experiment in mind?
Yeah, this is what I was trying to explain. So you could do it like this, no problem. And in this case, we would get 1, 2, 3 more Kirchhoff's voltage laws. And we could write them down, and at the end we would get a system of 6 equations for 6 unknowns. Our 4 currents and the 2 voltage drops across the current sources. And so now things are getting not complicated, yeah, but you also have alternative ways. And one rule that is written somewhere in textbooks says, okay, this complete tree should not go over a current source. So what would be another way to draw this complete tree? We could, for example, go this way. Right? It would be also a connection of all the 4 nodes without having a complete loop, and there is no current source inside this. Okay. And so now we would need to close this complete tree. And then there are more rules that say don't close it over ideal current sources. So we could close it here, but the only information that we would get from this equation is what is the voltage drop across this source. And we are maybe not really interested in this. It depends on, right? We cannot do something right or wrong. We can just find a maybe more easy way of solution. So we won't close it here because this is some ideal current source. We are not interested in the voltage drop because we just want to have this current there. We also don't close it here because we are not interested in this voltage drop. We will only close it this way. And if we just close it this way, we just get 1 Kirchhoff's voltage law for, let's say, for this loop here. And this will be our 4th equation that we need to set up a system of 4 equations for our 4 unknown currents. So I will switch back to, no, I will maybe write it in this color. So for this loop, yeah, Kirchhoff's voltage law would, how would it look like? Who can set up Kirchhoff's voltage laws?
You want to say V1 plus V2 equals V3 plus V4? Or?
Yeah, we can write it like this. So V1 plus V2 is the same as V3 plus V4. And of course, we always want to write it in a way that we want to have 0 or something like a source on the other side. There are no sources in this mesh equation or in this voltage law. So it's just 0. And for the voltages, I will now insert, it's always the resistance times the current. So R1 times I1 plus R2 times I2 minus I3 times R3 minus I4 times R4. Don't ask me why I've exchanged the order, but okay. It happened like this. So now we have 1, 2, 3, 4 equations for 4 unknown currents. And if we would have set up this complete tree in a different way, or if we would have also closed it via this mesh and this mesh, then we would get 2 more equations, and the 2 more equations would be there to calculate what is the voltage drop here and there. And it's also right, but then we have more effort because we have a larger system of equations. Okay, so now electrical engineering is over. It's just a mathematical task now. Just we need to solve the system of equations. And as usual, I would suggest to write it down in this matrix form. So we have a matrix, square matrix with all the coefficients. Then we have this vector with our unknowns, which are I1, I2, I3, and I4. And then we have a right side of this equation system, some vector with sources. And then we can look at these coefficients here. So we have 1, 0, 1, 0 in this case, and here the source IS6. In the next equation, we have 1, minus 1, 0, 0, and IS5. IS5. So then we have 0, 0, 1, minus 1, and minus IS5. And in the last one, we have R1, R2, minus R3, minus R4, and 0. And so, of course, now this matrix somehow contains all the equations, all the values, the whole structure of this circuit. And to solve this system of equations, we, of course, once again use Octave. So I will try to make this a little smaller here. And maybe clear the command Q and now insert the matrix, and I will once again just call it matrix. And we need square brackets for this. And just insert all the coefficients and a new line we get with the semicolon. And yeah, so I will once again just write the resistors even if they don't have values yet. So there will be some error message, and I will insert the values. So this is 10, this is 20, this is 30, and this is 40. And so then our matrix looks like this, looks pretty similar to what I've written by hand. So then we need to have the sources. So IS5 is 5 ampere, IS6 is 6 ampere. And we need to put them into this source vector. And so there we have IS6 plus IS5 minus IS5 and a last 0. So yeah, I think so. So okay, there we go. Okay, also looks similar to what we have here, just with the values inserted. And yeah, so now we can solve this equation system, and solving this equation system once again works that we get our vector with the unknown currents by taking the inverse of this matrix multiplied with our source vector. And there we get all the values. And luckily, the first one coincides with what we calculated before here using this superposition method and procedure, which does not look too bad. And so the other ones, without doing a formal proof, also don't look too bad. So how could we check if this works?
Do the superposition for the others.
Yeah, do the superposition for the others. Or now, if we have currents, we could of course also calculate voltages. And if we have voltages, we could check Kirchhoff's voltage law, for example. So if we just take these currents, so take this current vector and multiply it with a vector that contains all the resistors, R3 and R4. So now we get all the voltage drops across the resistors, because I've always calculated I1 times R1, I2 times R2, and so on. And so now we have the voltages on the, let me maybe go back to this here. So now we have the voltages here and there and there and there. So the sum of the first two, I will just do it by numbers. 72 plus 44 gives us something. And on the other side, minus 33 plus 150 and 2 also gives us, luckily, the same. And this is just what we had written down before. This is, I've now just checked this calculation here. So this perfectly works fine. And yeah, of course, we would need to check also the other Kirchhoff's current laws if they work, but we have not made a mistake. I propose. Okay. Any other ideas, comments, questions related to this task?
Just got an understanding question for setting up the Kirchhoff's voltage law.
Yes.
So theoretically, if you say the source still exists, you could also go. You never go over the source, you say?
Yeah, you can go over the source, but if you go over the source, then you get the voltage drop across the source as an unknown into your system of equations. And so if we would set up a Kirchhoff's voltage law going over the source, then we would at least end up with one more equation. So it's not, as said, it's not wrong, but it just increases the effort. And so this would be what we have done now would be I would not say the most effective way, but is an effective way of solving this if we just want to have currents, or if we just want to have one of these currents, and if we still want to use branch current analysis. And as said, it would be not wrong. You could also use this other complete tree and write down two more Kirchhoff's voltage laws for the two unknown voltage drops across the current sources.
In this case, it's also exactly the same, because in the first time you have the voltage with the plus, in the second time you have the voltage with minus. So if you sum up, it's the same.
Yeah, and it's like yesterday. So if we would write down Kirchhoff's voltage law for this small mesh and one for this small mesh, then they would both include the voltage drop across the source. And if you would take the sum of both Kirchhoff's voltage laws, then exactly this, the voltage drop across this source would cancel. Wait, we could quickly write it down. I think it's not too complicated to do it. Yeah. So if we would write a Kirchhoff's voltage law for this mesh here, so for this it would be that if we, let's say, start here, we go in the same direction as V3, we go in the opposite direction as, but okay, we would need to define what is the voltage drop across the source, and usually we would say current and voltage at sources point in opposite directions. So if we call this V5, then here we would say, okay, this is V3 plus V5 and minus V1, and this is 0 at the end. And if I take another color, maybe this one here, and if we set up a Kirchhoff's voltage law for this mesh, then it would be minus V5 plus V4 and minus V2 equals 0. And so now if we would take the sum of the two, and for this I can once again use this color. So if we take the sum of them, so plus V5 minus V5 is 0, then we have minus V1 minus V2 plus V3 plus V4. So I could write it down like this. And this is the very same that we had before, if I bring this to the other side. And so I said this would be, if you would draw the complete tree as we had before, and if you would close it over this mesh and this mesh, you would get two equations. But if you just take the sum of the two equations, you could eliminate this unknown voltage that you maybe want to have, maybe not. In our case, we would not like to have it. So don't be afraid there is no right and wrong. Yeah? If you set up Kirchhoff's voltage laws, if you set up Kirchhoff's current laws, if you insert Ohm's law, it will always somehow work. There are just more efficient and less efficient ways in calculating such circuits.